Hello guys, welcome to this video series on linear algebra for engineers. So in last class, we talked about vector spaces and subspaces. In today's video, we'll talk about dependent and linearly independent vectors. And some other things. Apart from this, we'll also be solving some exercise problems related to vector spaces and subspaces that we discussed in the last video. So let's start with some exercise problems. Exercise 1. So let V be a vector space, and whenever I say vector space, I mean vector space over K, where K is R or C. Now, is it true that negative of V is equal to V for every vector? Let's see. So let's prove this. So what we have to prove is this statement, and let's write this statement in words. What this statement says is that inverse of, because recall that from our last video, negative of V means the inverse of V. So this can be written as inverse of inverse of V is equal to V, right? This is what we have to prove. Now, how to prove this? So what we can do is we can see what this gives. Now we know that minus V is nothing but minus 1 dot V. We did this exercise in the last video. So this can be written as minus 1 dot V plus 1 dot V. This is a vector space property that 1 dot V is equal to V. So we have used that here. Now I can use the distribution properties to obtain minus 1 plus 1 dot V, and minus 1 plus 1 is nothing but 0. And 0 dot V is 0, as we saw in the last video. So what does this mean? It means something plus something is 0. So by definition of inverse, we can say that minus of minus V is just V. So this proves the statement, right? Now let's solve the second exercise. Okay, so one more thing before I proceed to the next exercise. Note that here I should actually write this because these are vector elements. And to merge two vectors, we have to use the binary operation, which we denoted earlier by this symbol. But here, since we are adding two numbers, we're not going to use this. This is to be used only when we are combining two vector space elements. Now, what I'm going to do is that I'm going to remove this symbol just for convenience. So now we'll be using this symbol and it will be clear from the context whether I mean this or this. Right? So let's not write this anymore. Let's write this everywhere. And which one is meant will be clear from the context. Okay. Let's move on to exercise number 2. So A belongs to A and V belongs to V. Now A dot V is 0, then A is 0 or V is 0. So let's prove this. So if A is 0, then there is nothing to prove and we are done. And if A is non-zero, then 1 by A is non-zero. Now, given that A dot V is 0, we can multiply both sides by 1 by A to obtain this, right? And here we can use the associativity to obtain 1 by A into A dot V. No dot between these two elements, this and this, because these are just numbers. We are using dot between a scalar and a vector. And here both are scalar. So what is this? This is nothing but 1. So we have 1 dot V equal to 0. But 1 dot V is nothing but V. Why? Because we proved it in the last video. 1 dot V equal to V. Oh, sorry, we did not prove it. It's actually a vector space property. So by vector space definition, right? It is from the definition. Okay. So we have proved that in this, if A is non-zero, then V has to be 0. Okay. Now let's see some more examples. Exercise number 3. See, you have a set U equal to x1, x2, x3 from R3. such that x3 equal to twice of x2 plus p. What is R3? R3 is Euclidean space, as I discussed in the last video. In space. Now, U is a vector space, or I should say a subspace of R3 if and only if B equal to 0. So can you solve this? Okay, so let's see. U is a subspace of R3. Let's prove. So clearly U is a subset of R3. This much is true. Now, in order to check subspace, what we have to do is we have to first of all check if the binary operation of R3 is applicable on U or not, right? That is, if I take first is binary operation check. So take x1, x2, x3, and y1, y2, y3 from B. Now apply binary operation of R3 on them. What do you get? You get x1, x2, x3. Apply binary operation of R3. You get this x1 plus y1, x2 plus y2, 3 plus y3. Now, is this resultant inside U or not? If it is inside U, then we should have this condition satisfied. So let's see if it is satisfied or not. See, 2x2 plus y2. Is this true or not? Let's see. So x3 is equal to 2x2 plus b because this guy is inside U. So it must satisfy this condition. X3 equal to 2x2 plus b. So we have this. Similarly, we have this y3 equal to 2y2 plus b. Using these three equations, what do we get? We get so we are getting y3 equal to 2y2. Okay. Using this here, we are getting y3 equal to 2y2. But we have y3 equal to 2y2 plus b. So using these two, we get p equal to 0. So for binary operation to make sense inside U, we need to have b equal to 0, right? So if U is a subspace of R3, then binary operation was solved. Binary operation of R3 must hold on U. That is, two elements taken from U must be combined to produce an element which lies inside U. Right? And for this to happen, we need to have B equal to 0. So we have proven this side, that is from here to this side. Now, other side is easy. So here, assume B equal to 0. Now we need to prove that U is a subspace. We need to prove this. How do we prove that? First of all, we check binary operation, and you can see that binary operation on R3 is applicable on U. You can check that. Second thing that we have to see if U has identity or not. So identity of R3 is 0, 0, 0. But 0, 0, 0 also belongs to U. So identity is satisfied. And the third thing is inverse. So if x1, x2, x3 is inside U, then you can see that this is the inverse. And this inverse is also inside U. So it's a vector space, right? So U is a subspace of R3. So this proves the result. Okay, now let's move on to dependence and independence of vectors. But before that, let's take a look at some terminology. So let's define first what is linear combination. Okay, so first let's simplify the condition for subspace a little bit. So how do we know if U is a subspace of V? How do we check that? Well, so first thing that I said earlier was to see if binary operation on V is applicable on U or not, right? Let's simplify this statement even further. So we call this closure property. Closure property. Closure under addition. What does this mean? It means for every U and U dash inside U, U plus U dash should be inside U. What is plus? Plus is binary operation on V. C dot U is also inside U. For every C in K, that is for every scalar C, right? So we'll just check these two things to determine if U is a subspace of V or not. So this simplifies our earlier check on subspaces. Now let's take a few examples to see the power of this. Look at this set x1, x2, x3. So this is in R3, that is the Euclidean space, such that x2 equal to twice of x3 plus b. So we need to show that U is a subspace of R3 if and only if b equal to 0. So how to prove this? Let's see. So, so first of all, let's assume that U is a subspace of R3. So in this case, this condition should be satisfied. That is, Cu should be inside U for every C in K, that is for every scalar. So if I take C equal to 0, that is number 0, and some x1, x2, x3 inside U, right? Then C x1, x2, x3 equal to 0 should be inside U. 0, 0, 0. They should be inside U, right? Since it is inside U, this condition should be satisfied. That is 0 should be equal to 2 times 0 plus b. And this means that b equal to. So we have proven one side. Now for the converse, we assume that b is equal to 0. Right? Now we prove that U is a subspace of R3. Again, we'll use this result. This is a very important result. We're going to use it a lot of times. So first thing that we have to check is closure, right? Closure under addition. So let's check closure under addition. So for that, what we do is that we take two elements, say x1, x2, x3, and y1, y2, y3. So take x1, x2, x3, and this another element in Q, right? Now check if the addition is inside U or not. So what is the addition? This is x1 plus y1, x2 plus y2, x. Is this inside U? How do we know if it's inside U or not? We have to verify this thing. So let's see. That is this middle one should be equal to twice of third one plus b. And what is b? B is 0. So we have to check if this condition is being satisfied or not. Is this true or not? So b is 0, x2 plus y2 equal to 2x3 plus 2y3. We have to check if it is true. Now, note that since this is inside u, we have x2 equal to 2x3 plus b, but b is 0. So we have this. Similarly, y1, y2, y3 inside u. So we have y2 equal to 2y3. If we add these two, then we get x2 plus y2, 2x3 plus y3. That is this thing. So this condition is true, and therefore u is closed under addition, right? So first condition is satisfied. Now we need to verify the second condition. What was the second condition? Take any scalar c and take any vector. Let's take x1, x2, x3 inside u. Then c dot x1, x2, x3. That is cx1, cx2, cx3 should be inside u. Is this true? Let's see. So since x1, x2, x3 is inside u, we can say that this is the condition, that is 2 times x3 plus b should be equal to x2, but b is 0, so this is equal to 2x3. Now multiply both sides by c, so we get cx2 equal to 2cx3. That is, this vector is inside u, right? So we can say that this is true. Okay, so 1 and 2 both are satisfied, therefore we can say that u is a subspace of R3 using the result. So this is the result. U is a subspace of V, then closure under addition, and this, right? Let me make it stronger. U is a subspace of V if and only if this happens. Okay. So we have shown that this condition is satisfied and this condition is satisfied, and therefore U is a subspace of V. So U is a subspace of R3 in this case. So yesterday I asked you a question, and the question was, is empty set a vector space or not? So did you think about this? Well, so empty set contains nothing. It's a set that contains nothing. That is, empty set does not contain identity element, identity, that is zero vector, It doesn't contain zero vector, but we know that a vector space must contain zero vector. An empty set does not contain that zero vector. Why? Because empty set does not contain anything. Empty set is empty. So it doesn't contain identity. Therefore, it is not a vector space. Empty set is not a vector. Okay. Now let me define something called span. Definition. So suppose v1, v2, v3, vn, they are vectors in some vector space V. So we define span of v1, v2, vn as the set of all linear combinations of vectors v1, v2, vn. Now, what is linear combination? So let me explain that. Then we'll get back to this definition. Definition. So again, suppose that v1, v2, vn are vectors in some vector space V. And I've said this before, when I say vector space V, I mean a vector space V over K, where K is either R or C. So what is the meaning of this? So linear combination of V1, V2. What is the meaning of this? Well, it means an expression of this form. C1, V1, C2, V2, Cn, where these C1, C2, Cn are scalars. That is, they belong to K. So whenever you see this kind of expression, C1, V1, C2 plus C2, V2 plus Cn, Vn, it means that it's the linear combination of V1, V2, V3, right? So, okay. So now let's come back to this definition. The set of all linear combinations of V1, V2, V3. So in set form, we can write it like this. C1, right, plus C2, 2, Cn, Vn, such that these C1, C2, C3, Cn are scalars. So this is fine. And second thing is, this is part of definition, span of empty set What do I mean by that? Well, so here you can see that we have span of n number of vectors. There are n vectors. So span of n vectors. Now, span of empty set means span of zero number of vectors, right? So this means span of zero number of vectors, right? So here we had span of n number of vectors. Here we have span of zero number of vectors. So we define this as the zero space, right? So zero space is actually a vector space. We define it as the zero space. So span of empty set or span of zero number of vectors is the zero space. Now let's note one thing. Why I define this span is because it's a very important subspace of V, right? So span is a vector space, right? It's actually a subspace of V. Can you prove this using the result that we discussed earlier? Yes, it's very easy. First thing we have to check is closure under addition. Closure under addition. So for that, take two elements, 2 V side this span, right? What this means is that there exist scalars C1, C2, Cn, D1, D2, Dn, such that U equal to C1 V1 plus C2 V2 plus Cn Vn, right? Because what is span? Span is the set of all linear combinations. So U is a linear combination of these. Similarly, V is a linear combination of these V1, V2, V3, Vn. So V equal to V1, V1 plus D2, V2 plus Dn, V. So what is U plus V? U plus V is C1 plus D1, V1, Cn plus Dn, V. But what is this? This is again a linear combination of, right? So this is linear combination of V1, V1, right? That means it belongs to span of V1, V2, V1. So closure is satisfied. Closure is satisfied. That is, we can say span of V1, V2, Vn is closed under addition. And second thing that we have to check is the scalar multiplication part. That is, So take scalar C, then look at Cu. What is Cu? Well, U is equal to this. So Cu is equal to Cc1 V1 plus Cc2 V2 plus dot 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 Ccn. But this is again a linear combination of these VI's, right? So this is also in span because span is the set of all linear combinations of V1, V2, Vn, and therefore this condition is also satisfied. So we can say that U is closed under scalar multiplication, right? Or by U I mean span. So span V1, Vn, right? So span is a subspace of V, V1, Vn. So you see how powerful this result is. This result is so powerful, right? So let's give this number two also a name. So the first one was called closure under addition. Let's call the second one closure under scalar multiplication. Multiplication. Okay. So span is a vector space. Fine. That is not number one. Second thing that we want to note is span is actually span of V1, V2, and is the smallest subspace that contains V1, V2, Vn, right? What is the meaning of this? It means, what is the meaning of the smallest? So we know that span is a subspace. So this part is clear. And we also know that this span contains V1, V2, and Vn. This is also fine. This is okay, right? You understand why span contains V1? Well, because V1 is a linear combination of these, isn't it? V1 is equal to 1 times V1 plus 0 times V2 plus 0 times Vn. So it's the linear combination of V1, V2, V3, therefore it is in span. So span contains V1, V2, V3, Vn. What is the smallest? So let me explain that. It means the smallest subspace means that if U is a subspace that contains these V1, V2, V3, Vn. So U is a subspace which contains V1, V2, V3, Vn. Then span is contained inside U. Span of V1. This is the meaning of this, right? So do you understand why the smallest, this word here, the smallest is justified? Because you take any subspace which contains V1, V2, Vn, and you'll find that span is sitting inside it, right? So any damn subspace U which contains V1, V2, V3 also contains span. That means span is smaller than U, right? Span is smaller than any U, any subspace, and therefore it is the smallest, right? And why is it that? Can you prove it? Let's see. So suppose U is a subspace which contains V1, V2, V3, Vn, right? So V1 is inside U, V2 is inside U, and Vn is inside U, right? Since U is a subspace, since U is a subspace, so C1, V1 is inside U, C2, V2 is inside U, Cn, Vn inside U. These C1, C2, C3, Cn are scalars. But since U is a subspace, the addition, it is closed under addition, right? So this addition is also inside U. But what is this? A linear combination of V1, V2, V3, Vn. And C1, C2, C3, Cn can be anything, right? C1, C2, C3, they can be anything. So span of V1, V2, V3, Vn is subspace of U. Because if you take any element from span, then it will look like this: C1, V1, C2, and this is already inside U. Therefore, span is a subspace of U. So this proves it. Okay. Now let's take a look at some examples. Span of 1, 0, 0, 1 is equal to what? So these 1, 0, 0, 1 are from R2, Euclidean space R2. So let's see. What is span? 1, 0, 1. It means the set of all linear combination of these two vectors, that is C1 plus C2 0, 1, such that C1, C2 are real numbers. So this gives you C1, C2 Let's C1, C2 are real numbers. But what is this? This is isn't this R2? Isn't this the plane? So we are taking all the points on the plane, and this is R2. So span of this is nothing but R2, right? Let's take another example. Is it true that 1 comma 2 is inside span of 1 comma 0, 2 comma 0? Is this true? Well, if it were true, then we would have 1 2 equal to C1 plus C2 2 comma 0. And this gives C1 plus 2C2 0. And if you equate both sides, then you get 2 equal to 0, which is not possible. So this is not true, right? No, it is 1 2 is not inside the span of these two vectors 1 comma 0 and 2 comma 0, right? Let's note another definition. So if u equal to span of v1 v2 vn, then we say that v1 v2 v3 vn span. So here we use the verb span. We say that v1 v2 v3 vn span u. For example, we saw earlier that 1 comma 0 0 comma 1 span which set r2, right? Because remember that span of 1 0 and 0 1. We saw it earlier, right? We saw it here. Okay, so let's take some more examples. Look at this set P2. What is P2? Let me denote it like this. What is this? It is the set of all real polynomials of degree less or equal to 2. Recall it from our last video, last to last video. I think it was last video on vector spaces, where we showed that this is actually a vector space. So this is a vector space. Now, question is, can you find what spans this space? Well, I say that 1, so 1 is inside P2, right? 1 is inside P2. And polynomial x is also inside P2. And x square is also inside P2. right? Now, I say that span of 1 x x square is actually p to x. Do you agree or not? Let's see. So we have to prove this. We want to prove this. We want to prove this statement. How do we prove that these two spaces are equal? So whenever we have to prove two sets, so whenever we have to prove two sets A and B are equal, how do we prove them? We show two things. Number one, A is a subset of B, and number two, B is a subspace of A. That is, A is contained in B and B is contained in A. So this shows that both are equal. This is the technique, and we're going to use the same technique here. So let's show that span of 1 x square is inside V2x. To do that, take a polynomial fx inside span 1 x square. So this means there exist constants or scalars, say c1, c2, c3, such that fx is equal to c1 plus c2x plus c3 x square. But this is a degree 2 polynomial, and therefore it lies inside V2x. So fx lies inside V2x. That is, span of is actually a subspace of V2x. Now we want to show the other side. Now we want to show that V2x is inside the span of 1 x and x square. How do we show that? Well, we take any element inside V2x. So take take a plus bx plus cx square inside V2x. But this is a linear combination of 1 x and x square, right? Where is a times 1 plus b times x plus c times x square. This is a linear combination of 1 x and x square, right? Therefore, it is in the span. So we have proven that p2x is in 1 x x square. So we have proven this, and we have proven the other side as well. Therefore, we have proven this. So this is, that is 1 x and x square span p2x. So 1 x x square span p2x. Okay. Now let's move on to linear independence of set. So linearly independent vector definition. So vectors v1, v2, v3, v4, vn are said to be linearly independent in V if the only scalars for which C1 V1 plus C2, or let me rephrase it differently. V if for every scalar C1, C2, Cn, C1 V1 plus C2 V2 plus Cn Vn equal to 0 implies that C1 equal to C2 equal to 0, right? Cn equal to 0. So all the scalars are 0. That is, whenever you get this condition, so whenever you have C1 V1 plus C2 V2 plus Cn Vn equal to 0, then you can immediately write C1, C2, Cn all are 0 if these V1, V2, V3, Vn are linearly independent. This is the meaning of linearly independent vectors. So this is linearly independent, and if V1, V2, Vn are not linearly independent, then we call them linearly dependent. Let's take a look at some examples to better understand. So 1, 0, 0, 1 are linearly independent in R2. Why? Because if you write this, see, we are writing this condition equal to 0, then you should get C1, C2 both equal to 0. So C1, C2 equal to 0, that is this 0 on the right hand side is 0 vector. So what we get is C1 equal to C2 equal to 0. So see, this condition is satisfied. This is giving this, right? Therefore, these are linearly independent in R2. Now, let's take another example. How about 1, 0, 0, 1, and 0, 0? So these are linearly dependent. Why? Let's see. So if I write this now, see, let's write C3. Then what do we get? So this term is 0, right? So we get this only. And this is giving us C1 equal to C2 equal to 0. But what about C3? C3 doesn't have to be 0, right? C3 is not necessarily 0. C3 is not necessarily 0. I mean, you could take C3 equal to 2. Still you get C1 and C2 both equal to 0. But C3 is non-zero. So C3 may be non-zero, right? But what we want is that all have to be 0. None of them can be non-zero. Therefore, these are linearly dependent. Okay. Now, let's take some more examples. How about 1x and x square in P2x? They are linearly independent, right? Why? Because you write C1 into 1, C2 into equal to 0, right? So we have written this. Now we need to see what C1, C2, and C3 are. So this is true for all x, is true for all x, right? But this is actually a quadratic equation, isn't it? This is actually a quadratic equation. And quadratic equation has two solutions, right? That is, they should hold only for two values of x. It is x equal to x1 and x equal to x2. But it is true for all x. What does this mean? This means that all have to be 0. So C1 equal to C2 equal to C3, all equal to 0. Therefore, 1x and x square are linearly dependent vectors inside P2x. Okay, now let's move on to another definition. So if U is equal to span of V1, V2, V3, Vn, that is U is spanned by a finite number of vectors, then U is said to be finite dimensional, right? So here U is spanned by n vectors, that is finite number of vectors. So U is finite dimensional. Otherwise, infinite dimensional. So let's take a look at some examples. Recall that R2 is equal to span of 1, 0 and 0, 1. So R2 is spanned by two number of vectors, 1 and 2. It is spanned by two vectors. So we say that R2 is finite dimensional. Now let's take a look at this. Px. What is Px? It's the set of all polynomials, set of all polynomials, all real polynomials. That is, coefficients are real. The set of all real polynomials. So this is a vector space. You can check that this is a vector space. So check Px is a vector space over R. Now you'll ask me, if it's a vector space, then what are the operations that you're considering? Well, I'm considering the usual addition and the usual scalar multiplication. So this is a vector space. Now, is it finite dimensional or infinite dimensional? So see, 1 is inside Px, x is inside Px, right? And x to the power n is inside Px. Okay. So if it is, let me put it this way. If Px is finite dimension, so that is Px is equal to span of some polynomials, right? Polynomial P1, polynomial P2, and polynomial some Pk, right? Some k polynomials are there and they span Px. Let's say if this is the condition. Now look at the polynomial with the highest degree. So let's say P2 is the polynomial of highest degree. Let's say its degree is n. Its degree is n. That is, it will have x to the power n term inside because its degree is n. This is the highest degree in all these polynomials. That means x to the power n plus 1 is not inside any of these polynomials. This term is not inside in any of these polynomials. But we know that x to the power n plus 1 is a polynomial which is inside. So it is not inside this span, but it is inside this polynomial, right? Therefore, it can't be finite dimensional. So it is infinite dimension. Let's see some more examples. So look at these vectors u and 2u inside v. Are they linearly independent or not? These are linearly dependent in v. Let's see how. So look at this. I write 2 into u minus 1 into 2u. And what do I get? I get 2u minus 2u equal to 0. So C1u1 and C2u2, let me write it like this. And C2, so C1v1 plus C2v2 equal to 0, but these are non-zero, right? This is non-zero. This is also non-zero. Therefore, they are not linearly independent. Therefore, they are linearly dependent in V. So that is the meaning of linearly dependence actually. That is, one is linear combination of the others. That is the meaning of linearly dependent. So here you can see 2u is just 2 into the first vector. That's why it is linearly dependent. Anyway, let's move on. Let's take a look at the result. V1, V2, V3, Vn. These are linearly dependent. Linearly dependent. Then there is a Vk. There is an element Vk here among these vectors, which can be written as linear combination of the vectors which are coming before it. That is, there exists k in 1, 2, 3, 4, 5, n such that Vk equal to span of vectors which are coming before it. That is V1, Vk minus 1. This is the meaning of this. Okay. So this is one thing. And the second thing is, if you remove this Vk, then span doesn't change. That is, span of V1, V2, say Vk minus 1 here, Vk, or let's just write Vk here, Vk and Vn. Remove this Vk and still the span will remain same. So here you have Vk minus 1 and then Vk plus 1 because Vk is removed and Vn. This is the result. We're going to need this result in lot of calculations. They're going to simplify our calculations a lot. For example, you can do magic like this. So span of 1 comma 0, 0 comma 1, right? This is same as span of 1 comma 0, 0 comma 1, 1 comma 1. Why? Because see, this vector is in span of these. This is just equal to this plus this. So this vector is in span of these. So if we remove this, nothing happens to the span. And here we removed it. We removed this, knocked it out, and the span remains unchanged. Right? Now let's note another result as well. So in a vector space, in a finite dimensional vector space, set of any linearly independent vectors, right? If you take its length, set of any linearly independent vectors, if you look at the size of this or the cardinality of this, you'll find that it is always less or equal to set of spanning vectors. What do I mean by this? I mean that if V is equal to a span of say U1, U2, and UM, right? Then U1, U2, UM are spanning vectors because they span V, so they are spanning vectors. So how many of these are there? M. And if say V1, V2, Vk are linearly independent in V, then how many of these are here? K. Then what I'm saying here is that K is less or equal to M. That is, spanning vectors are more than linearly independent vectors. So if these are linearly independent in V and these are K in number, then K has to be less or equal to M. This is a very powerful result. It's going to save you a lot of computations, lot of calculations. Let me show you how. Let's take a look at an example. Say 1, 2, 3, 4, minus 2, minus 1. So these vectors are linearly dependent or independent in R2. Now, to check if these are linearly dependent or independent, what you have to do is you have to write C1 of C1 first vector plus C2 second vector plus C3 third vector equal to 0. Then you have to solve this and see if you're getting C1 equal to 0 or not. This is a tedious process, right? So here you have vectors in R2, but imagine if you were given vectors in say R4 or R5, the computation will be lengthier. But this result saves you the calculations. How? Let's see. So we know that R2 is a span of 1, 0 and 0. Okay. How many vectors? Two vectors. So if they were linearly independent, then how many of these are here? Three. Then as per result, 3 should be less or equal to 2, right? But this is not true. So they can't be linearly independent. They have to be linearly dependent, right? Linearly dependent. See, calculation saved. So this is the power of this result. I want you to remember this, right? You're going to use it a lot. And its proof is also very easy, actually. So, but let's not get into the proof. The proof uses this result actually, but let's not get into that. For now, let's just understand how to use these results to our advantage. Okay, now let's take a look at another definition. So, span, spanning vectors, right? So, spanning vectors, we know that what spanning vectors are. These are the vectors which span a subspace under discussion. So, spanning vectors for vector space U, that is the vectors which span U. Now, spanning vectors can be linearly dependent or independent, right? For example, look at this. R equal to span of 1001. This is same as span of 100111, right? This is using the result before. This is a linear combination of these two. Therefore, this is linearly dependent, and we can remove this guy and the span will remain unchanged using the result that we did here. Using this result, right? So note that this is a set of spanning vectors. So 1001 are spanning vectors, but these are also spanning vectors, but these are linearly dependent and these are linearly dependent. So spanning vectors can be linearly dependent or linearly dependent, right? So let's note a definition here. If A, V n span V and are linearly independent, then we say that this set V1, V2, V3 is a basis of V, right? And V1 to Vn are called basis vectors of V. So here 1001, these are basis vectors of R2. For example, 1001 is a basis of R2, okay? Because they span R2 and they are linearly independent as well. Okay, let's choose a notation here because it's difficult to write them again and again. So even means column vector with 1 in the first slot and 0 in the remaining slot. Similarly, E2 is 1 in the second slot and 0 in the remaining slot. We'll use these notations even and E2. So even E2 are basis vectors of R2. Even E2, this set is a basis of R2. And similarly, we can say that 1 x x square is a basis of P2, P2x, right? This is a basis of P2x. So these are called even E2. See, these are obvious basis of R2. These are kind of obvious. We call them standard basis. So even E2 is called standard basis of R2. Standard basis of R2. So does a vector space have only one basis, or a vector space can have many bases? It can have many bases. See, for example, 1 0 0 2 is also a basis of R2, right? So you can check this. How will you check this? First of all, you'll show that this spans R2. And second thing, these are linearly independent. That's it. You're done. So this is also a basis of R2. But you can see that it is different from this basis, right? But what is common in both these is that both have two number of vectors. This has two number of vectors inside, and this also has two number of vectors inside. Even though they are different, but the number of vectors in them seems to be the same. This is in fact a result. So let's take a note of this. A vector space V can have many bases. So when I say V, I mean here finite dimensional vector space. V can have many bases. This is so we have taken a note of this because here and here we're getting different bases. But there is a result which says all bases of V finite dimensional, right? This is finite dimensional vector space. All bases of V have the same number of basis vectors. Same number of basis vectors, right? What is the meaning of this? It means that if U1, U2, U is a basis of V, right? And V1, V2, Vm is a basis of V, then n equal to m. Okay, so this is the meaning of this. Why? Why is it true? Let's see. Let's see. So since U1, U2, U3, and U1 is a basis of V, we can say that V is equal to span of U1, U2, Un. How many vectors? N vectors, right? There are n vectors. Now, V1, V2, V3, Vm is also a basis. That is V1, V2, V3, Vm are linearly independent in V, right? So they are linearly dependent in V, as you can see here. by the definition of basis. What is the meaning of basis? It means span and linearly independent as well. So since this is linearly independent in V, we can use the result that we discussed earlier, that number of linearly independent vectors is less than spanning vectors. You remember that? Let's go back. Let's keep going. Look at this result. Set of any linear independent vectors, length of set of any linear independent vectors is less or equal to length of set of spanning vectors, right? So we can say that here, so these are m vectors, right? So m is less or equal to n. This is our equation 1. Now v1, v2, v3, vn, they are so this is the basis of v. So we can say that v is equal to span of v1, v2, v3, and vn, m, vm, right? But now u1, u2, u3, un is a basis of v. That is u1, u2, u3, un are linearly independent. So un are linearly independent in v. So the length. So how many of these are here? N. How many of these are here? M. So I can say using that result, n is less or equal to m. This is our second equation. Use equation 1 and 2 and tell me what you get. So 1 and 2 give n equal to m, right? This was easy, wasn't it? That is, all bases of V have the same number of basis vectors. Therefore, this number becomes important. So this gives rise to our next definition, right? So number of elements in a basis of V is called the dimension of V, right? See, I'm using the article the here. Why? Why I'm using the? Why not the? Why not a dimension here? Because we have seen that if we take any basis of V, whether you take this basis or this basis, they're going to have the same number of elements in them because n is equal to m, right? That's why the dimension, because it's unique. So let's end it with some examples of dimension and then we'll continue in our next video. R2 is a two-dimensional vector space. So we've been calling R2 a finite dimensional vector space, but now we've become more specific. Now we're calling it a two-dimensional vector space because dimension of this R2 is 2. Why? Because if you take a basis of R2, take this basis E1, E2, the standard basis. How many vectors are there? Two vectors. So its dimension is 2. So this is a basis of R2. Now, an exercise problem for you, which you can answer in the comments. tell me dimension of P2x. So P2x is our friend that we met earlier in this video and in the last video as well. So thank you so much for watching this video. We'll be meeting in our next video. Bye bye and take care. Thanks.